In this problem, we're asked to calculate the mole fraction of Cl- in the solution, and given the three quantities we have underlined here, we can calculate the moles of chloride ion and also the total moles of everything in the solution. Our total moles are going to be dictated by the concentration of the calcium 2 plus, the concentration of chloride, which is going to be twice that of Ca2 plus, and then also the water that composes this solution. And keep in mind, we have 375 grams of water for 23.7 grams of calcium chloride. So the major component of this solution is going to be the water. So let's take our 23.7 grams of calcium chloride, convert that to moles, then convert from moles of calcium chloride to moles of chloride to give 0.427 moles of Cl-. We can then calculate the concentration or the number of moles of Ca2 plus from the moles of Cl-. There are 2 moles of Cl- for 1 mole of Ca2 plus. So the amount of moles of calcium 2 plus is going to be half that of the chloride ion. We're also having 375 grams of water. We convert times its molecular weight to get 20.833 moles of H2O. So you can see here, when we look at the total number of moles, that it's mainly composed of water in this solution, and we have 21.47 moles of total solution. We then can calculate the mole fraction, which is going to be the moles of Cl-, which is 0.427, divided by 21.47394, which ends up giving us 0.199 as the mole fraction of chloride, which the closest answer here is going to be 0.200, which is the correct answer. Next, we're going to look at a solution containing 15 grams of KCl in 1,650 grams of water, and we're going to determine its freezing point. Pure water has a boiling point of 0 degrees Celsius, and when we create a solution, that freezing point is going to lower. So the lowering of the freezing point depends on the quantity and not the kind or identity of the particles dissolved in solution. So we need to figure out how many particles we have in solution, and we can then use the formula delta TF equals I times M times KF. The molality of this solution is going to be the moles of the KCl per kilograms of water. We can convert our 15 kilograms of KCl to moles using its molar mass, and then divide by 1.6500 kilograms of water. That gives us a molality of around 0.12. So in order to determine the Van't Hoff factor I, that's the number of particles we have in solution. KCl will dissolve into 1 cation and 1 anion, since the charge of K plus is +1 and Cl minus is -1. So that's going to be a value of 2. We multiply that times the molality we calculated, and then put in the 1.86 degrees Celsius per molal for our Kf. That gives us a delta TF of 0.4476, which will give a value of negative 0.45 degrees Celsius. Because remember, this is a freezing point depression. So when you're typically given a problem like this in a multiple choice fashion, you will see both the positive and negative numbers there. And what we need to do is determine which one of those is correct. Okay, it's freezing point depression, so it's going to be the delta TF is going to be a negative number. Next, we're looking at a 0.100 molal solution and figuring out which one of these solutions will have the lowest vapor pressure. Vapor pressure lowering is the colligative property, and as we increase the number of particles, we're going to decrease the vapor pressure. So here we have 5 different substances where we create a solution, and we need to look at the Van't Hoff factor I for each one. NaCl is going to break down into Na plus and Cl minus, so I is 2. KClO4 has K plus and ClO4 minus, so I is also 2. Sucrose does not break down, so its I value is going to be 1. AlClO4 3 times is going to give us 1 aluminum 3 plus and 1 ClO4 minus, so that has an I value of 4. And CaClO4 twice is going to have an I value of 3. So based on each of these values, we can say that the highest value for I, which will give us the most number of particles, is going to be for our aluminum compound. Okay, so now we have the most particles here, and we're going to have the lowest vapor pressure, because the colligative property is vapor pressure lowering. So AlClO4 3 is going to be our correct answer here. The next question deals with the concentration of NO2 dropping from 0.0198 to 0.00779 in 292 seconds. So we need to calculate the rate of disappearance of NO2 over this time period. The rate of disappearance is going to have a negative, the change in concentration of NO2 divided by the change in time. We're given the values of 0.198 and 0.0779. We'll subtract those two, divide by 292 seconds, and our rate is going to equal negative 4.11 times 10 to the minus 5 molar per second. In this problem, we were asked to calculate the rate of disappearance of NO2, but we can set a rate expression for any reactant or any product in this particular reaction. So our rate is going to equal negative 1/2 times the concentration of change in concentration of NO2 over the change in time. That's going to equal positive 1/2 change in concentration of NO per time, which would equal the change in concentration of O2 as over the change in time. And for each of these, we can set equalities up to do one of two things. One, we could calculate the overall rate of the reaction, or we can now do calculations that compare in, say, the change in concentration of NO2 versus the change in concentration of O2. And the change in concentration of O2 will be twice as much as that of NO2. One other thing to mention in this particular problem, our correct answer here is 4.11 times 10 to the minus 5. We calculated our rate to be a negative number. Just make sure that you are very careful in reading the questions, especially when you're based on kinetics problems. Here we're calculating a rate of disappearance, and that rate of disappearance is going to imply that negative sign. So the rate of disappearance is going to be 4.11 times 10 to the minus 5, whereas the overall rate would be negative 4.11 times 10 to the minus 5 molar per second. Our last question is going to kind of build on some of the concepts from the previous question, and we're here asked to calculate the concentration of S2O8 2- remaining at 400 seconds. So we can write our rate expression to be negative 1/1 times the change in concentration of S2O8 2- over the change in time is going to equal negative 1/3 times the change in I- over the change in time. If we're looking at an average rate, we can use the stoichiometry of the chemical equation to look at a concentration at a particular time interval. We can rearrange this expression because we're calculating for the change in the concentration of S2O8 2-. We can get rid of the negative signs, and if we rearrange this a little bit more, the delta T, since it's the same time range, that's going to cancel as well. So the change in the concentration of S2O8 2- is going to equal 1/3 times the change in concentration of I-, which, given in the problem, was 0.072 minus 0.057. So therefore, our change in concentration of S2O8 2- over our 400-second time interval is going to be 0.005 molar. We're not asked for the change in concentration, we're asked for the concentration of S2O8 2- remaining after 400 seconds. So we need to take the initial concentration, which is 0.05, subtract 0.005 molar, and that's going to give us 0.045 molar for the concentration of S2O8 2- remaining after 400 seconds.